Okay, here we are. Things are going to get very interesting as we near the end of the semester. So let's start with something familiar. Here's a wire, the red thing with current going in this direction, and it's in a magnetic field which is into the page. So what happens when I turn the current on? Okay, you know how to do this. Right hand rule number 1, F equals L ILB. How does your thumb point? Up. So the wire moves up, right? So you put current in, the wire moves up. So supposing we put a weight on here. Put current in, the wire moves up, it lifts the weight. Oh, we're doing work. Ha-ha. So by putting electricity through this wire, the wire can move something. So what is that? It's a motor. That's the foundation of any motor. You put current through what's going to be a coil. It's going to spin, it's going to turn an axis, it's going to turn some gears, and it's going to do work for you. Okay, now let's turn this around. Let's take the wire and lift it up here and move it down. So just imagine, I wonder if I can do that. Let me pause the video. Okay, now I can move the wire, right? Just a wire. Whoops, just a wire, no current in it. So I move the wire down. I move the wire into the field. Just a wire, right? I move it into the field. What happens? Pause the video and figure it out. Don't be lazy. Figure it out. Need some help? So think about the electrons in the wire. They're free to move. So the electrons are moving down in a magnetic field. What do the electrons do? Pause the video, figure it out. Okay, when the wire comes down, the electrons are moving down. So an electron moving down with a field into the board, the force, the right-hand rule says, the right-hand rule gives us my thumb pointing the force, my thumb pointing in this direction, but it's electrons, so the electrons go this way. Electrons going that way means what? Means currents going this way. Or if the positive charges were free. So you see what we have? Put current through the wire, and the wire moves up. Take the wire, that's the motor. Whoops. Take the wire and move it down, and then what do you get? You get current through the wire. What is that? You move a wire into a magnetic field and you get current. Oh, that's something. That's a generator. Only when we come to study it, you'll see that for a motor, we spin a coil in a magnetic field. Using current, we spin a coil in a magnetic field, and that coil runs a motor. Or if we spin the I said it backwards. If we put current through the coil will spin and do work. If we spin the coil, if we crank it, right, we have this over here. If we actually crank the coil in the magnetic field, it generates current. Okay, so that's what we're learning about this week. Faraday and Lenz's law. Okay, we're not in class, so I can't demo this live, but I would do this in class. Take a magnet, hold it near a coil, don't move it, nothing happens. Move the magnet into the coil, you get current in one direction. Move the magnet out of the coil, you get current in the other direction. So stationary, nothing happens. But if you move a coil into a wire, it generates current. So this is another way of thinking about a generator. Except usually we spin a coil because this motion is a little clumsy. It's easier to spin something in a magnetic field, right? So the way we understand this phenomenon is stated in Faraday's law, or a way of understanding it is stated in Faraday's law. So here it is. Faraday's law says you will get an induced EMF whenever you have a changing magnetic flux. So what we did there was we were moving magnets back and forth, something was changing. So Faraday's law focuses on the change in flux through a loop or a coil. And if you're sticking a magnet into a coil, it is going to be proportional to the number of windings, no surprise. So let's just remember what flux is. Electric flux was E dot dA, so magnetic flux is B dot dA, which is B times A times the cosine of theta. Hopefully you have a memory of that idea of flux. It's the number of field lines which passes through an area element. Or to say it another way, you can visualize it by visualizing the number of field lines passing through an area. And how much passes through an area element will depend on the direction those two vectors are facing, right? It's a dot product. So if we bring that up here, we have dBA cosine theta dt. So we can get a change in flux by changing the magnetic field. Usually that's constant. We can get a change in magnetic flux by changing the area of the coil. Usually that's constant. What usually we change is the direction, right? So here's a coil in a magnetic field, and we spin the coil. So the direction of the area element as it spins is constantly changing, and that generates a constant output, a constant EMF. Oh yes, remember, EMF means electromagnetic force. It's an induced voltage, right? This is units of voltage. And I think we used this symbol before, but maybe we haven't in a while. So that's Faraday's law. Let's apply it to a few situations. Oops, I forgot. When we use Faraday's law, we always use it in conjunction with Lenz's law. So if we have a changing flux, it's going to induce an EMF, and that induced EMF, in many cases, not always, gives rise to a current. And if we have, supposing we induce an EMF in a coil, that gives rise to a current in a coil. That means there's a magnetic field in the coil, and that means that there's a changing flux in the coil due to the EMF we produced. So what's the direction of the EMF, the current, the field? So it always, Lenz's law tells us that the induced EMF will always produce a field and a flux which opposes the change that's producing it, or tries to keep the original. Okay, this won't make total sense until we apply it to things, but you can think of it like electrical inertia, right? Opposes change, resistance to change. So or keep the original. So if an object's in motion, it tends to stay in motion. If you're going to change it, you need an outside force. So that's how this works. So we have Faraday's law, Lenz's law. Now we'll apply both of them together. Okay, here's an application. We have a magnet, and as the arrow indicates, I'm moving the magnet in. So this is a flux to the left. So that could induce a current in either direction. We might not be sure. So if it induced a current in that thing which was clockwise, using right-hand rule number 3, that means that the current would produce a field in the same direction as this field, and the induced current would take the increasing flux and increase it more. So if you think about that, that would be a violation of conservation of energy. It means as I move this in, the change would produce a change that would be a positive feedback, whereas the opposite happens, a thing that's consistent with conservation of energy. The current induced is counterclockwise. That current gives rise to a field in this direction, And so the increasing number of field lines entering this coil are offset or canceled, partially canceled by the field in this direction. On the other hand, if we move the thing away, now we're decreasing the flux. We're not increasing it. We're taking a field like this and taking it away. So the change would be to maintain the original flux, not to let the flux decrease. And so in that case, you would in fact have a current in the opposite direction, clockwise, which would produce field in this direction, which would tend to keep the original situation. So again, if there's no flux and you try to increase it, it will oppose the increase. If there is flux and you try to decrease it, it will oppose the increase. There's another way of checking this that I'm going to show you right now. Okay, this is how it works. If I move this toward, this is a north pole, so what I said is I'm going to generate a counterclockwise current, which produces field lines in this direction, and a counterclockwise current means that this field lines going this way means that this becomes a north pole. And so as I try to move the magnet in, the induced EMF leads to a current, leads to a field, which pushes back on me. So as I try to push it in, I feel resistance. Okay, conservation of energy, that makes sense. In order to push it in, I have to do work. I have to do work to generate current. If it were the other way around, then as I push this in, if the field were in the opposite direction, as I pushed it in, I'd induce a current that would actually attract it and pull the magnet out of my hand, and that makes no sense at all. And the same thing happens over here. As I try to remove the magnet, I'm reducing the flux, so now we do get a clockwise current, which puts a field this way. So as I try to pull the magnet out, now this is the south pole, and so as I remove the magnet from the coil, the magnet sees the south pole. It means I have to pull on the magnet to get it out because it's being attracted back. So the induced field produces a magnetic pole. It always opposes the motion you're doing, and that's why we won't get to do this live in lab. When you crank a generator and it's not connected to anything, it's easy to crank. But once you hook it up to a device, a light bulb or something, and you try to crank it, it's much harder to crank because you get this Lenz's law effect. Here's another diagram that shows that. If I move, now I'm moving the south pole towards a coil. That generates a current in this direction. And this becomes the south pole. So as I move it in, the current creates a polarity such that it's opposing the motion producing the current to begin with. And when I try to remove it, the current goes the opposite way. This becomes a north pole, and now it's being attracted. So I have to push it to get it in to generate current. I have to pull it to get it out to generate current. And so all of that is consistent with our understanding of conservation of energy. Okay, let's take one more look at our motor and generator before we move on to something else. Here is the motor. A battery puts current through a coil. As the current comes out of the positive terminal and goes up this way, we have a current this way through a magnetic field in that direction. So if you do your right-hand rule, let's see, let me pause. Not the best figure for this, but if the current is going up, let's call this the y-axis and this is the x-axis, then when you use right-hand rule number 1, you get that the force on this piece of wire is into the screen. And when you do this, coming the other direction, you get that the force is out. So the force on this piece of wire is going into the screen. The force on this piece is coming out. And so this coil is going to rotate like that. and that's the motor. Unfortunately, you won't get to see all this in lab, but in this case, that a motor and a generator are actually the same thing. So if I take a motor and I put current in, it'll spin. If I take the same device and put a crank on the coil and spin the coil, current will come out. So a motor and a generator is the same device. It's just in one case you put current in and you get work out. In the other case you put work in and you get current out. So jumping back to Faraday's law, remember, you can vary B, A, or cosine theta. So far we've been varying cosine theta, but here we're going to vary B, not by actually changing the field, but we're going to slide a coil, so the area is constant, but the field going through the area is going to increase. And so we can use right-hand rule number 1, is the wire slides in this way, the charges in it are moving in that way, and the field is, does this make sense? Yes, it makes sense. I thought those were dots. They're actually X's. So the charges are going in the direction of the black arrow, your fingers pointing to the page, your thumb points up, and so the charges go up, so current goes this way. But let's use Lenz's law to figure it out. So as this slides in, the number of field lines going into the board is increasing. So the X's are increasing, and so the current goes clockwise, which leads to a field which is out of the board. So the field and the flux produced by the current is coming out at us. It's tending to reduce the increasing number of X's. So this is what you got to practice using Lenz's law. And the assignment has lots of situations to practice it. Okay, one final situation. These black lines are conductors. We'll say that they're rails, and they're lying on a horizontal surface. And they're connected with a resistor here. And then there's this bar that can slide, this black bar can slide back and forth across the rails. Let me see if I can fix that. Okay, I get it working. So these are conducting rails connected with a wire and resistor, and the red bar can slide back and forth across the rails. I think I can do that. Yep, see. So what happens is I slide this way. There's a conducting loop here, right? And as I slide the thing this way, the conducting loop gets bigger. So this is a case where we're varying the area of the loop, right? If I slide it this way, the area is getting bigger and smaller, and because the area is changing, the flux is changing. You can either look at the equation and see that here, or you can see that as I move this, the number of field lines is changing. Right now there's 4 X's, now there's 8, now there's 12. So I can increase or decrease the flux through the loop. This is going to induce an EMF in the coil, and there's a couple problems in the assignment like this. So let's just predict the direction. If I go this way, the number of X's is decreasing, so I have to induce an EMF and a current that's going to replace the loss of flux, and so you should get, using right-hand rule number 3, that would be clockwise. And if I move the bar this way, I'm increasing the number of X's. I want to oppose that change. I want to produce a current and a field that's going to come out of the page, and so that would be a counterclockwise current. And then we can actually derive an equation for this problem, which we'll use by looking at Faraday's law up here. Okay, so here it is, and I think we're done. This is the equation. You're going to use it in the assignment, BLV. See where it comes from. Follow this. So we start with Faraday's law, E equals minus n d phi dt. So for this, n is 1, right? It's just the two rails in the sliding bar. So we have dBA cosine dt, but the b is constant. We didn't vary the field, so that comes out. It's just the area that's varying. But we're not varying the length, we're just varying the width of the thing. And so the b and the l come out, and we have dw dt, but the rate at which the width changes is just the velocity of the bar. And so there you have it, and you're ready to go.